Hey guys, how's it going? It's going to be hard to top that last video over implicit differentiation, but we'll try with this one when we start taking the derivatives of logarithmic functions. Yes, logs want to play in these derivatives just like our exponents and our trig functions and our polynomials and our rational functions. Every type of function that we talked about last year in pre-calculus want to play with these derivatives, and logs are no exception to that. Okay? So I'm just going to give you this idea of how to take the derivative of a log function. And so if I'm taking the derivative of log base a of x, where a is just going to be a regular base down there, it is going to be 1 over x natural log of a. What's that? I couldn't hear you. Oh, you don't believe me? Oh, well, if you don't believe me, I'll be glad to prove it to you. Okay, so my definition of a logarithm says that if I'm taking y equals log base a of x, that is going to be true if and only if I have a to the y is equal to x. So if I take the derivative of this, I will get a to the y natural log of a and since I take the derivative with respect to y, that's going to give me a dy over dx right there equals 1. A little bit of implicit differentiation. You might be saying, well, where in the world did you get this derivative from? I'm kind of wondering that myself, but that's one of those special rules I told you that we had to have. So if we had something other than e to the y or e to the x, it followed into this differentiation. Okay. And so if I solve this, I get dy over dx equals 1 over a to the y natural log of a, which is exactly what I was trying to tell you. Oops, I got to plug back in. 1 over x natural log of a, since a to the y is equal to x. So if that's true, we don't see a lot of log base 10s or log base 7s. We see a lot of natural logs in calculus. So if that's true, whenever I'm taking the natural log of it, that would just be 1 over x natural log of my base. Remember, this is log base e. Well, natural log of e is just 1. So I luck out a lot whenever I'm taking the derivative of the natural log of x. It's just simply going to be 1 over x. So what we can do, we can use this idea with derivatives of log functions, along with other differentiation rules we've learned in this chapter. Just keep expanding to whatever we need to take the derivative of. So taking the derivative of natural log of x cubed plus 1. I'm going to go ahead and burst your bubble. I'm probably not going to ask you just to take the derivative of the natural log of x. I'm going to have it so you take the derivative of natural log of a function of x. So we're going to have a lot of chain rules on this, including this one. When I do a chain rule, derivative of the outside, derivative of natural log of something is going to be 1 over that something. And then chain rule says I just got to take the derivative of the inside now. And so the derivative of the inside part of this function would be 3x squared. And so when I write this all together, fly on my whiteboard. Oh, missed it. Oh, it's attacking me now. Sorry. It's going to give me 3x squared over x cubed plus 1, and that would be my derivative. Think you can try it? You give it a go. Okay, take a natural log of this trig function. You know what the derivative sign is. You know how to work the chain rule, so you go ahead and work it out, and then come back and see my work. So go ahead and hit pause. Did you take it all the way out to cotangent? I hope so. There's a reason we went over all those trig identities last year. And Let's do one where the natural log's on the inside. Again, I'm still looking at a chain rule on this. It's just now, natural log's not the derivative, I'm not going to be using the natural log, I'm going to take the derivative of the outside. Because my outside function this time is the square root. So you might want to think of this as the natural log of x raised to the 1/2. Now I see where I can drop that 1/2 down and lower the exponent by 1. And I get to take the derivative of the natural log of x now. The derivative of natural log of x is 1 over x. So if I just move everything to the bottom that needs to be on the bottom, well, if I had a 2 on bottom, I got an x on bottom. This has a negative exponent, so I'll just go ahead and move it to the bottom. And taking something to the 1/2 power is the same as doing the square root. And so this is probably going to be the answer that the book would give. These don't take very long, do they? Ooh, it's not natural log this time. So we're going to, again, this isn't going to happen a whole lot here. We do natural log a lot when we work these problems. So I'm going to have to go back up to let me write my rule up here. The derivative of log base a of x is going to be 1 over x natural log of a. So there's a little 10 right there. You guys already knew that. I didn't have to tell you that. So it's going to be 1 over, this is called, I think it's called the argument. So 1 over the argument. And I'm just going to multiply that by the natural log of 10. Now, unlike what I have here, I just was taking log base a of x. Here I'm taking log base 10 of a function of x. So I'm going to need to go ahead and do the derivative of this 2 plus sine x, okay, for the derivative of my inside. So whenever I do that, that gives me 1 over 2 plus sine x times the natural log of 10. And the derivative of 2 plus sine x, well, derivative of 2 is 0. Derivative of sine is cosine. I think if you just throw this cosine on top, it's going to be about all we do with it. That's it. Well, surely we can get a little bit harder, right? Oh, I said just a little bit. Okay, well, I'm always interested in how my students say to work this problem. And I usually just go with it. And there's one of two ways of working it. So the first way of working it, I can look at it as just a chain rule. So if I take natural log of this quotient right here, that would be the derivative of the outside would be natural log of something. That would be just 1 over that something, right? Times the derivative of the something. Well, the something is a nasty quotient rule. A nasty quotient rule. And there's a square root inside of it. So I'm going to have to use a chain rule whenever I take the derivative of the bottom. Well, let's just go ahead and go with it. So derivative of the top, look out there is 1, times the bottom, minus the top. All right, here we go with the derivative of the bottom. It's a chain rule. So I drop the 1/2 down in front, lower the exponent by 1. Ah, it's nice. My derivative of my inside is just going to be 1. So I'm done with that. And then whenever I square the bottom, I just get x minus 2. We can clean this up. I got fractions inside of fractions. Well, 1 divided by something is just going to be its multiplicative inverse. So keep, change, flip, whatever you want to do, that's going to flip to this quotient. All right, now cleaning all of this up, let's see, I get the square root of x minus 2. I've got minus x plus 1. Feels like I'm missing something here. And then I'll put that 1/2 out front. And I have the x minus 2 to the 1 half. Negative 1 half. Didn't really clean it up a whole lot. Just kind of flipped the front there. Got rid of some ones. Looking at this now, I see that, how do I want to clean this up? You guys have any ideas? You guys haven't talked very much today. I see that I'm just randomly changing stuff right there. That's kind of throwing me off. You guys not going to tell me about it? Okay, so if I distribute this square root of x minus 2 through, it just gives me an x minus 2 for that first term. I've got the 1 half. And if I distribute the x minus 2 to here, it gives me x minus 2 to the 0 power. Remember, this is going to be a 1 half. That'd be 1. So I just have this x plus 1 all over. Well, on the bottom, I would have x plus 1 and x minus 2. That looks a little bit better. I think I can go a little bit further with it. Let's see, I have x minus 1 half x. That's just going to be 1 half x. I have negative 2 minus 1 half. That would be negative 2 and a half, and negative 5 halves over x plus 1, x minus 2. Yeah, this is not fun at all, is it? I'm gonna get rid of my fractions on that. I'm just gonna say x. I'm gonna multiply everything by 2. X minus 5, and then there's gonna be a 2 there. That's about all I can do. I mean, even if I multiply and FOIL stuff, it's not going to clean up a lot. That was tough, and that's normally how my students in class tell me to work it. But I know good and well that my calculus class is normally full of pre-cal all-stars. And didn't I have a rule for whenever I was differentiating, not differentiating, but I was taking log of a quotient? I think whenever I took the log of a quotient, I could do natural log of the top minus natural log of the bottom. I'm going to change that to the 1 half power. Just do a bracket. You're saying, oh, I don't know what that's going to do. Good, I'm going to show you. I'm not going to differentiate yet. I'm still just using algebra right here. And I can bring that 1 half down in front. I had a power property for logarithms that allowed me to just bring that power down in front. I think I can take a derivative now. Okay? So I take the derivative of natural log of x plus 1. It's going to be 1 over x plus 1 times the derivative of x plus 1, which I look at as just 1. Minus 1 half. I take the derivative of the natural log of x minus 2. That's just going to be 1 over x minus 2 times the derivative of x minus 2, which is, again, just 1. Let's get a common denominator. Look at this common denominator. It looks so familiar. Algebra is here to help us, all right? So if I multiplied this denominator by, it looks like 2 times x minus 2. Bring down the minus sign. I multiplied this denominator by x plus 1. So sure enough, 2x minus x, that's x. Negative 2, oops, minus 1 is minus 5. So if you remember that algebra, man, it could make life a lot easier as far as taking the derivative of it. And as you can see, we got the same derivative either way that we worked it. So that'll take some practice, all right? Definitely will. So spend some time with it. And now we're going to look at differentiating the natural log of the absolute value of x. Remember, just the absolute value of x broke up into a piecewise function. So I want to do that with this natural log of x right here, because I know it's going to take on the value natural log of x if x is greater than 0. Let's not do 0, because I think that's going to give you something undefined. So just greater than 0. And it takes on the value of negative x if x is less than 0. Okay? So if I take the derivative, y prime, of both of these pieces, well, we said earlier that that's just going to be 1 over x if x is greater than 0. And if I take the derivative of the natural log of negative x, that's going to give me 1 over negative x times negative 1. Well, that's just going to be 1 over x. So I don't have to really worry about whether or not I'm taking the natural log of a negative or the natural log of a positive. If I'm taking the natural log of the absolute value of x, the derivative, let's see, how do I want to write this? The derivative of the natural log of the absolute value of x is equal to simply 1 over x. That seems really weird that I went way around this whole idea just instead of just telling you it's 1 over x. But I really need you to remember this fourth quarter. I'm going to say, hey, go back and look at the section where we differentiated logarithms. And maybe I'll remember it's example 6, but we really need that because something's going to happen whenever we try to work this in reverse. And we're going to have to come back to this example to fully understand why. That's pretty good for a first day. If you want to take a break, hit pause on it. I'm going to go ahead and go through and talk about something called logarithmic differentiation. We just took the derivative of logarithms. Now I'm talking about logarithmic differentiation and why we need to have it. So the calculation of derivatives of complicated functions that involve products, quotients, and powers can often be simplified taking logarithms. And whenever I do that, that is called a logarithmic differentiation. Can you imagine, we just spent a lot of time a couple of examples ago working out something like this. Instead of using my log properties, can you imagine taking the derivative of this? We definitely could. It would be a product rule on the top, a quotient rule over all, and look at the bottom, it's got a chain rule, as well as that square root would have a chain rule as well. We would be on this problem for a while. I'll tell you, I worked this out in not many lines at all on my notes using this idea of logarithmic differentiation. So what I did first was I took the natural log of both sides. So that gave me the natural log of y equals. Notice that this one didn't have a log in it to begin with. I'm introducing a log to it. That's the difference with logarithmic differentiation. And so using all my log properties, I know if I take log of a product that I can separate them with an addition sign. And I can also drop their exponent down in front. So that square root is being raised to 1/2 can drop in front. Oh dear. And I can take the, let me do this in more steps. I'm trying to cut way too many corners. I can do x to the 3/4 plus natural log of x squared plus 1 to the 1/2. And if it's on bottom, I can just subtract off natural log of 3x plus 2 to the 5th. Now the natural log does not distribute through those parentheses, but I have a power property that will bring all these exponents down in front. Hopefully you agree that's equivalent to what is above it, okay? Last year we spent some time expanding a logarithm. This is why. Is because I'm now able to take the derivative of all this, including the left side. I need to take the derivative of this natural log of y. So I'm going to bring back some implicit differentiation here. And I'm going to take the derivative of this whole right side in terms of x. The 3/4 just comes from the right. Derivative of the natural log of x is 1 over x. 1 half comes down for the ride. I have 1 over whatever I'm taking the natural log of times the derivative of my argument. 1 over the 3x plus 2 times 3. And so cleaning this up, this gives me 3 over 4x. It's not going to clean up a lot. They're not going to play well with each other, and we're not going to go through and try to find a common denominator. Let me make sure I'm in the right spot on this. Let's go ahead and cancel these 2's. I forgot about that over there. So we just have an x and an x squared plus 1. And we got 15 on top here, and a 3x plus 2. Don't worry about finding a common denominator on this, and this is actually going to be equal to y prime over y. So we have one more step that we need to do before we're done. We need to multiply both sides by y, because I'm wanting to differentiate this. I'm wanting an explicit formula solved for y prime. So if I multiply both sides by y, what I end up with is this 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. And then instead of y, I'm going to put down what y is equal to. Remember what y is equal to way up here? It's x to the 3/4 square root of x squared plus 1 all over 3x plus 2. That raised to the 5th. And that would be my derivative. Yeah, I know it's still pretty long, but it's way shorter than all those product, quotient, and chain rules I was going to have to use back up in the beginning. I don't think I would be able to fit it on the whiteboard, so it would have been much harder. So here's kind of the steps I used in it, okay? So if you didn't quite follow it, or if you draw a blank later and you don't want to go back and watch that whole last example, you can just follow these 3 steps, and that'll get you to the answer I got. Now, I want to remind you of the power rule. The power rule says if n is any real number, then remember what I can do in order to find f prime. Oh, it's been a long day. F prime of x. I can drop the n down in front and lower the exponent by 1. Now, you guys just kind of believed me on that. I'm going to show you why that works now, just in case you were skeptical back then. We kind of just did some patterns where I showed you, oh, just check it out. I'm dropping the number down front, lowering the exponent by 1. I want to show you now why that is working. Because if I take the natural log of both sides, that's going to allow this n to drop down to the front. And if I take the derivative of the natural log of y, that gives me 1 over y, y prime, which would just be y prime over y if I multiply it. If I take the derivative of this, remember n is just going to be a constant, so n is just hanging out. So that's just going to be 1 over x for the derivative of the natural log of x. Well, that's just going to, like I said, n over x. And so, whenever I multiply both sides by y, remember that I multiply both sides by y is simply equal to x to the n. So I'm multiplying by y, multiplying this by y. I end up with, let's see, that's going to be n over x times, my y is equal to x to the n. Let me rewrite that a little bit. That's going to be n times x over n over x. The first, meaning that I have the same base, I can just subtract their exponents, and my derivative would be exactly what I told you many, many days ago. That was free. You don't have to worry about paying me for that or anything. That was just wanted to show you where that came from. Okay. So there's many uses for this logarithmic differentiation besides proving our most basic differentiation rule. Okay. So let's go over these. We're going to assume a and b are constants on this. X is going to be my variable x, and I have functions of x's, f of x, and g of x. So if I'm just looking at differentiating two constants, or not two constants, but say it's like 7 to the 5th power, yeah, I'm just differentiating a constant. That's going to be a 0 right there, because a and b are constants. If I am wanting to differentiate a function raised to a power, that's going to be my chain rule, where I drop my constant, my power down in front, lower the exponent by 1, put some brackets around it, and then multiply it by the inside. Definition of my chain rule right here. If I have a number raised to a power, according to my rule on that, it's just going to be the number raised to the power. I introduced this back when we did e to the x. I think it was 3.1, so you can go back and look in the videos and find that if you want to. And then I just multiply that by my g of x. Everything is being multiplied there, my g prime of x. But here's where I'm going to need to use logarithmic differentiation. I'm not even going to write out how to do that. I'm just going to put logarithmic differentiation. Because I'm going to end up wanting to take the natural log. I can take the natural log of this, the g of x can then dump in front, and then I'm just left with a product rule. Okay? You will have a chain rule with it, but I think we can get it. Let's take a look at it. We're going to start pretty basic. So I have a function of x raised to the power that is a function of x. So I think if we use logarithmic differentiation, we can make life a lot easier. I mean, we haven't even seen a rule for handling something like this. So we're going to force it into a rule of something that we've seen. So I'm just using algebra so far. If I take the natural log of one side, I got to take the natural log of the other side. And then I'm ready to use calculus. I take the derivative of natural log of y, gives me 1 over y prime, which is just y prime over y. Okay, this is where I lose a lot of people right here, especially on the upcoming assessments, is I give them a couple of these, and they just throw all of their differentiation rules out. I have the product of two functions of x. I have to use my product rule on this part. So, derivative of the first times the second plus the first times the derivative of the second. Alright, so we'll go back to red. So what's that going to give me? When I multiply both sides by y, we'll multiply all this by y. I'm going to clean up all of this in here. So that's going to be natural log of x over 2 square roots of x, right? Plus, well, square root of x over, let's think about this, square root of x over x would be x to the 1/2 over x to the first. Subtract their exponents. It's going to be 1 over x to the 1/2. So this is going to be 1 over the square root of x right here. Multiply by my y. And so I've got to bring him down. That's part of my answer. And that would be it. The book gives an alternate way of working it. If that was confusing, you can definitely go back and read it. Rewatch the video, or maybe get it from a friend explaining it to you. It's kind of a weird idea to go with. The number e is a limit. I'm going to skip this in my video. We don't really need it going forward. It's really cool how it works. If we have time in class, I definitely want to cover this. But for now, I'm going to try to get under 30 minutes on this video. And so I'm going to just assign these problems. These take practice, guys. And it's all cumulative. You got product rule, you got power rule, you got quotient rule, you got chain rule, you got logs. Everything's in here. So very good practice set right here. It's a lot of problems, but we'll spend some time in class going over it. Have a good one, and I'll catch up with you guys next time.